Okay, so so far whatever little bit theories are there for resonance, we have seen it. Now we'll take a simple example, right? So this is a simple series RLC circuit. This is RL is given and this is 320 picofarad. And if you want instantaneous polarity, you can take plus minus, and this voltage is 0.85 volt, right? So this is simple RLC circuit. What you have to do it? So it is written in next. So this is example 1, that you have to determine the value of L for your what you call for resonance if Q is equal to 50, right, and F0 is equal to 175 kilohertz. Also find the circuit current, the voltage across the capacitor, and the bandwidth of the circuit, right. So this is the problem. This is the circuit, and this is what you have to determine. Everything is given here, right. So first thing is, we know that resonance frequency F0 is equal to 1 upon 2 pi root over LC. So F0 is given 175 kilohertz. So it is 175 into 10 to the power 3 is equal to 1 upon 2 pi root over your what you call C is given 320 picofarad, 320 into 10 to the power minus 12 into L, from which you will get L is equal to 2.58 millihenry. Right. Now we know that XL is equal to L omega. So L we have got it 2.58 into 10 to the power minus 3, right, it is in Henry, into your 2 pi into F0 is equal to 175 into 10 to the power 3 hertz, right. So that means XL is equal to L over this much of ohm. So it is 2840 ohm, right. So quality factor Q is equal to omega 0 L upon R, right. So omega 0 your what you call this omega 0, that means R is equal to omega 0 L upon Q, right. So here you just substitute your all these values. So you will get your R is equal to 56.8 ohm, right. So this way actually your L you have got, that is your 2.58 millihenry, and your here your F0 is given this one, right, 2 pi F0. One thing is there, one correction is here. Here it is your omega 0. So omega 0 is equal to 2 pi F0, right. I think 2 pi is missing, right. Just check this answer. I think this answer is correct. Perhaps I missed this one. It will be omega 0, right. So Q is equal to your 50. Q is equal to 50 is given. So R is equal to omega 0 L upon this thing. This you please check it, right. Hope this is correct. So next this one R you have got. Then the impedance of the circuit of the resonance is that at the resonance XL is equal to XC. So Z is equal to R. So it is 56.8 ohm. So I0 is equal to V upon R. So V is given 0.85 volt divided by R. So 14.96 milliampere, right. So and also VC is equal to I0 upon omega 0 C. So this means it is RI0 by numerator and denominator you multiply by R. RI0 upon omega 0 CR. So that means VC is equal to QV, right. So that means if you your what you call, we know that your RI0 is equal to your what you call RI0 is equal to V, and omega 0 CR, that is 1 upon omega 0 CR is equal to Q. So it will be Q into V, right. Therefore voltage across the capacitor will be 50 into 0.85. V is 0.85 volt and Q is 50. So 42.5 volt. And bandwidth is omega 2 minus omega 1, or it is radian per second, or F2 minus F1 in hertz, right. So Q we know, we have derived this. Q is equal to omega 0 by omega 2 minus omega 1 is equal to, you can write F0 upon F2 minus F1 is equal to F0 by bandwidth. Therefore bandwidth is equal to F0 by Q. When you take in terms of F0, it is in hertz. So 175 into 10 to the power 3 divided by Q is equal to 50. So 3.5 say kilohertz, right. So bandwidth. Now example 2. So this is a simple example, right. Only thing is that this your what you call here I told you, just see it is omega 0 actually 2 pi into F0. I might have missed 2 pi. Just check the answer, right, whether it is 2 pi is taken care of not, right. So it is getting 56.8. just check. So this one, your next is for the circuit shown in figure, that R1 is equal to, I will show you the circuit. R1 is given 0.5 ohm, R2 1.5 ohm, and R3 is equal to 0 ohm. C1 6 microfarad and C2 12 microfarad, L1 25 millihenry and L2 15 millihenry. So determine the frequency of the resonance, that is first one. Second one, Q of the whole circuit, and 3 Q of coil 1 and Q of coil 2 individually. So this is my series circuit. This resistance is given 0.5 ohm. This is coil 1, its resistance is 0.5 ohm, inductance is 25 millihenry. These two capacitors are there in series, 6 microfarad and 12 microfarad, right? And this is the coil 2, resistance is 1.5 ohm and inductance is 15 millihenry. This is the problem. So now question is the impedance of the circuit. So L, this your 25 millihenry and 15 millihenry. Find out the total equivalent, or what you call L. So it is 25 plus 15 means 40 millihenry, right? And these two capacitors are in series, means it is equivalent to the way you obtain the resistance in parallel. So it will be 6 into 12 by 6 plus 12, right? So this will be 4 microfarad. So C is equal to 6 into 12 upon 6 plus 12, it is equal to 4 microfarad. And then your what you call, that we know that F0 is equal to 1 upon 2 pi root over LC. So it is 1 upon 2 pi, L we got 40 millihenry, so 40 into 10 to the power minus 3 into 4 into 10 to the power minus 6, the capacitor for 4 microfarad. So this actually will get F0 is equal to 10 to the power 4 by 8 pi hertz, or omega 0 is equal to 2.5 into 10 to the power 3 radian per second, either in hertz or in radian per second, right? So now Q of the whole circuit, it will be L omega 0 upon R, right? So L, we have got your what you call that this thing omega, your this is your L 40 into 10 to the minus 3 whole circuit. This is correct. 2.5 into 10 to the power minus 3 10 to the power 3 radian per second is equal to, actually this will become 40, is equal to 40. So this is not there, right? This is my class note, so all corrections made. Actually same thing I have scanned it here for you, right? So this is 40, right? So this is correct. Therefore this is not this thing, this is actually 40. It is written here, corrected, it is 40, right? So Q of the whole circuit is 40, right? So let me clear it. So then this one, that Q of coil 1, it is L1 omega 0 upon R1. For the coil, omega 0 is 2.5 in 10 to the power your what you call this omega 0 is equal to 2.5 in 10 to the power 3 radian, this thing your what you call, it is radian per second, it is given here omega 0, and L1 is equal to your this one L1 here, L1 is equal to actually this one 25 millihenry, right? So here this one, it will be your let me correct it, it will be your L1 is equal to 25, not 2.5, right? So in this case this answer is not 12.5, it will be actually 125, right? So just check it, let me make it, it is half, right? So it is 25, so this is cancelled, right? And this is 2 means 5, so answer will be 125, right? So this is not 12.5 because it is 25 millihenry. By mistake I took it, but this is my class note, everything is corrected actually, right? So similarly L2 omega 0, L2 is 15 millihenry, and that is 15 10 to the power minus 3, and it is omega 2.5 in 10 to the power 3 upon R2 is equal to 1.5, right? If you calculate it, right? So just if you calculate it, it will be 25. So please check all this by little bit of calculation, all these things you please do it of your own, right? See that all calculations are correct. So bandwidth is, we know we have done it, bandwidth is equal to F0 upon Q, right? So your what you call, you substitute your all these things. F0 is equal to, we have got it 10 to the power 4 upon 8 pi hertz. So here it is 10 to the power 4 upon 8 pi, and Q is equal to whatever you have got, right? Q is equal to your overall thing is 40. This Q we got is 40, right? It is 40. So it is corrected here, it is 40, right? So if you do it approximately, it will become 10 hertz, right? So this is the bandwidth. This is not 125, huh? This is 40 because we got it, this is 40. So this will be approximately 10 hertz. So this is one. So another one is example 3. A coil having a 5 ohm resistor is connected in series with a 50 microfarad capacitor. The circuit resonates at 100 hertz. That means your F0 is equal to 100 hertz. A, determine the inductance of the coil. B, if the circuit is connected across a 200 volt 100 hertz source, determine the power delivered to the coil. And now C, the last one, last but one, voltage across the capacitor and the coil, voltage of the capacitor and the coil, and D is the bandwidth of the circuit. This is the thing you have to find it. When you read this video lecture, first you note it down, right? Then you solve the problem. So and your what you call, So circuit you can do of your own, circuit is not done, it is very simple thing, right. So at resonance omega 0 is equal to 1 upon root over LC, that we know. So 2 pi f0 is equal to 1 upon root over LC. So f0 is given 100 Hz and C is given 50 microfarad. So 50 into 10 to the power minus 6 farad, and it is L. So L will become 50. So solve it, it will be 50 millihenry. Now the current at resonance will be V upon R, because XL is equal to XC. So the current is maximum. So 200 by 5. So current is 40 ampere. Right. Now power dissipated is I square R. So 40 square into 5. So 8000 watt is equal to 8 kilowatt. Right. So voltage across capacitor. Voltage across the capacitor is the magnitude IXC. Right. So I is 40 ampere and XC is equal to 1 upon omega C. C is equal to 50 microfarad. So 50 into 10 to the power minus 6 farad into 2 pi into 100. So it comes around 8000 by 2 pi volt, right. Approximately this is your 1273.2 volt. This is not this thing, this is the correct one, 1273.2 volt, right. So the impedance of the coil R plus JL omega. So it is 5 plus J, L is 50 into 10 to the power minus 3 into 2 pi into 100, right. So it is 5 plus J 31.4 ohm. So VL is equal to I into your Z. So it is 40 is the current we have got, into this Z we will get its magnitude is 1256 volt. We have taken its magnitude only, that your what you call this, and angle is not written here, right. So our interest is magnitude only. So this one actually it will be multiplied by 40, just check it, right. Then root over 5 square plus 31.4 square, whatever it comes, just check, it will be 1256 volt, right. Only magnitude written here. This is actually if I make it, I should make it bar. The magnitude is taken here, 1256 volt, right. So now Q of the coil will be equal to your what you call, it will be 31.4 by 5, right, because it is XL is 31.4, right, and R is 5, so it is 6.3, right. It is basically your what you call the Q0 of the coil. So it is XL is basically is L omega by R. So L omega is actually 31.4 divided by R is 5, so 6.3, and bandwidth is equal to F0 upon Q0. So 100 upon 6.3 is equal to 16 Hz, right. So this is the simple thing. Now example 4, a series circuit with R is equal to 50 ohm, L is equal to given 0.05 Henry, C is 20 microfarad. So and has an applied voltage V is equal to 100 angle 0 volt with a variable frequency. Frequency is a variable here. Find the maximum voltage across the inductor as the frequency is varied. You have to find out the maximum voltage, right, across the inductor as the frequency is varied. Now Z is equal to root over R square plus L omega minus 1 upon omega C square, that is XL minus XC square. Therefore current I is equal to magnitude V upon magnitude of the current root over R square plus L omega minus omega C square whole square, right. So magnitude of the voltage across L is VL will be I into L omega. We want only magnitude, so that means XL is actually it is I into XL. So XL is equal to L omega. So it will be omega L V upon root over R square plus L omega minus omega C whole square. So setting the derivative dVL upon d omega 0, you take the derivative of this equation 1 with respect to omega, right. So and what we call and set it to 0 and solve for omega, we will obtain the value of omega when VL is maximum, right. So that means dVL upon d omega is equal to this one. It is simplified and written to the power minus half. You please do a little bit of your own. I mean, what is there? This your XL minus L omega whole square, it is expanded, right, and put it is square root there. So it is to the power minus half, right, because it is your omega L V upon root over this one. So it is to the minus 1 upon half. Then you take the derivative. If you derivative and simplify, you will get R square minus 12 upon C plus 2 upon omega square C square is equal to 0. You will get it. That means omega is equal to 1 upon root over LC into root over 2 upon 2 minus R square C upon L, right. But we know, we have derived it, that Q0 is equal to omega 0 L upon R, that we have done, is equal to, we know, 1 upon omega 0 CR, that also we have done. And if you if you multiply Q0 into Q0, you will get Q0 square is equal to 1 upon R square C. This also we have derived. That means this term is r square, then if the reciprocal of this one, r square c upon l is equal to 1 upon q0 square. So here you put 2 minus it will be 1 upon q0 square, right. All these things previously derived. So that means my omega will be is equal to, upon substitution, 1 upon root over LC 2q0 square upon 2q0 square minus 1. So the equation 5 shows that for a high Q, the maximum voltage your across L occurs at your this omega 0 approximately 1 upon root over LC. If Q is very high, then 2q0 square, right, your what you call minus 1 approximately 2q0 square, right. So this one, after if q0 is very high, so this term will become unity. So in that case it will be omega upon 1 upon root over LC. So that is your approximate value 1 upon root over LC. Now if Q is high, maximum voltage are also obtained across R and C at omega 0, that is a resonance frequency, right. So with low Q, Vc maximum occurs below omega 0 and VL maximum occurs above omega 0. This is a small exercise to you. We look at the expression, and with low Q, Vc maximum occurs below omega 0 and VL maximum occurs above omega 0. This is an exercise, small exercise for you, right. Already we have done it for resonance. Now from equation 2, so omega is equal to, we can simplify, write root over 2 upon 2 LC minus R square C square. That is from this equation. That is from this equation only. This is equation 2. From equation 2 you can write like this. So you can write like this. So C, R, L, all values are given. You substitute all these values. If everything is given, you will get omega is equal to 1414 radian per second. This is the answer, right. When you take dVL upon d omega is equal to 0, this is the answer, right, for which voltage across the inductor will be maximum, right. So XL is equal to L omega 70.7 ohm, X0 is equal to, XC is equal to 1 upon omega C 35.4 ohm. Please calculate all these things, and Z will be then R plus J your XL minus XC. So whatever it comes, it is 61.2 angle 35.3 degree ohm, right. Therefore I is equal to V by Z, the magnitude, that is 100 angle 61.2, so 1.635 ampere, right. So all these things you please calculate. Directly I have substituted after getting omega, right. So you just make this calculation. Therefore VL max will be I into your XL, that is your what you call, that is your 70.7, right. So you will get 115.5 volt. This example is very interesting one, right. So this is the VL max. Now example 5, in this case this parallel circuit is there. This is an inductive circuit, so 8 plus J6 ohm, and this is your capacitive circuit 8.34 ohm, but this C is varying, XC is varying. You have to find C which results in a resonance when omega 0 is equal to 5000 radian per second, right. So in this case this problem is very simple. It is omega 0 is given, so it is a parallel circuit. So Y is equal to 1 upon 8 plus J6 plus 1 upon 8.34 minus JXC, right. So this is the Y. So now you just your what you call, this one you multiply numerator and denominator by 8 minus J6. Here also numerator and denominator you multiply by 8.34 plus JXC. Then you simplify, you will get this is the real part and this is the imaginary part, and at resonance this imaginary part will be 0, right. Therefore if this part is 0, then XC upon 69.5 plus x square minus 6 upon 100 is equal to 0. If you solve it, right, you will get the two values of XC. One is not feasible, so XC is equal to 8.35 ohm, that is equal to 1 upon omega 0 C, right. So if you solve now, that your what you call, the omega 0 is given 5000 radian per second, it is given, suppose C is equal to, you will get 24 microfarad, right. This is the answer. Now next one is determine RL and RC for this circuit, RL and RC, which causes the circuit to be resonant at all frequencies, right. All frequencies means that we have derived that your what you call 1 upon root over LC into multiplied by some factor. No, if I recall now, I am not going that, hope I will write correctly. If I recall correct that it is root over LC, say omega is equal to, then the factor that your RL square minus L by C divided by RC square minus L by C, something like this. If RL square is equal to RC square, right, is equal to L by C. So it actually resonates all the frequency, because this square root term, it will become actually 0 by 0, undefined. So it will, the circuit will, resonance will happen at all, in all frequencies, right. Further, you have to find out what is the RL and RC based on this condition. The answer is not given here. I didn't intentionally, I didn't write the answer. So please do it. When you will do it, you let us know the answer. I'll tell you the correct answer, or put the thing in the forum, right. So with this your resonance part is over. So some typical example we have seen. After that, very simple thing it is, that is the maximum power transfer theorem for DC circuit we have seen. So for AC circuit also very simple it is. We will see the maximum power transfer theorem. Concept is from the DC we have already studied. So AC only we will see little bit. So this is the maximum power transfer theorem for AC circuit. Now there are three cases. So case 1, load, right. The variable resistance is RL. Suppose this is my voltage source VG is given for a circuit, plus minus polarity is marked, current flowing through this is I, and this is ZG is equal to say RG plus JXG, impedance is given, and this RL is variable, right. In the case of DC circuit, it was a DC supply, and this was also your what you call, that is your R Thevenin, and this was V Thevenin in the case of your DC circuit. So here also suppose this is given, and then what will be the value of RL for the maximum power transfer theorem, right. So if you see the current magnitude, I will be equal to VG upon, assuming that angle is 0, VG angle 0, right. If you, I mean, there should not be any confusion anywhere, right. This will be VG angle 0 degree, but we are taking the magnitude. So current is I is equal to VG upon this is the series impedance together. So RG plus RL plus JXG, right. So this is my current magnitude. Now your what you call, therefore your this one, just hold on, this is actually given in phasor. This is actually, then you put angle 0 degree, because VG I told you angle 0 degree. This is a phasor because we have put J. So it is a phasor quantity, not magnitude. Now when you take the magnitude, you take the absolute, right. It is VG upon root over RG plus RL square plus XG square, right. So this is the magnitude. Therefore power actually across RL, power loss across RL is magnitude I square into RL. So this square means VG square into RL by RG plus RL square plus XG square, right. Now for maximum power transfer theorem, dP upon dRL is equal to 0, right. If you make it 0, you will get RL square, you will get RG square plus XG square. That means RL is equal to root over RG square plus XG square, and that is equal to magnitude of ZG, because ZG was given RG plus JXG. So its magnitude ZG is equal to root over it is capital R, root over RG square plus it is also capital X, G square, right. So that's why RL is equal to root over magnitude of ZG, right. And for like your, if XG is equal to 0, like your DC maximum power transfer theorem, so naturally R is equal to your RG. There we do V Thevenin, R Thevenin. In that case it was RL is equal to R Thevenin for DC circuit. Here also similar thing. So this is actually for, that means for this circuit you have to keep it in mind, for this kind of circuit RL will be root over RG square plus XG square, that is mod G, right. But never be RL is equal to RG, right. It will be root over mod G, root over RG square, it is mod G, root over RG square plus XG square, RL is equal to, right. So this is your RL. So now case 2, then in this case that is impedance ZL with variable resistance and variable reactance. So here also or what you call, this is also my VG angle 0. Angle is not shown here, polarity is shown here, and this is suppose ZG is equal to RG plus JXG, right. It is something like your V Thevenin and Z Thevenin, say. This is the current I, and this ZL is variable, both RL and XL are variable, right. So that's why that is the given here, impedance ZL with variable resistance and variable reactance, both are variable. So we have to find out the value of your what you call the impedance, right. So now current I is equal to VG upon, then you add RG plus RL plus JXG plus XL, like your series circuit, whatever you do. So this is my this thing. So magnitude of the current I, your what you call, here one this thing is there, this should not be there. right. So it is Vg upon your what you call, and here if you want you can put this one, Vg angle 0. So so magnitude of I is equal to Vg upon root over Rg square plus RL square plus Xg plus XL square, right. Now P is equal to your I square RL is equal to Vg square RL divided by Rg plus RL square plus Xg plus XL square. So this is equation 1, right. So let me, so this is not a, this is here I corrected it, here I forgot. So this is not there, Vg upon this one, right. It is understandable to you. So now if RL in equation 1, this equation is held fixed. Suppose RL we are fixing it, say RL is held fixed. The value of P is maximum when Xg is equal to minus XL. So if you set Xg is equal to minus XL, that means Xg plus XL is equal to 0. So this term will vanish, therefore power will be maximum if RL is held fixed, right. So that in that case the value of the P is maximum, because Xg minus Xg is equal to minus XL means Xg plus XL is equal to 0. But this term will not be there. So in that case it will be Vg square upon RL by Rg plus RL square if RL is held fixed. So that means equation 1 will become your Vg square upon Vg square into RL upon Rg plus RL square. This is equation 2, right. Now if you consider now RL to be variable, right, like the way you did in DC circuit, RL to be variable. As shown in case 1, the maximum power is delivered to the load when RL will be equal to Rg. There also is said for the first case that Xg is equal to 0, then RL is equal to Rg. In that case, your what you call that, and XL is equal, therefore the maximum power is delivered to the load when RL is equal to Rg. If RL is equal to Rg and XL is equal to say minus Xg, then ZL is equal to RL plus JXL. Here in the circuit, that ZL is equal to RL plus JXL, and here you put XL is equal to minus Xg for maximum power transfer theorem. So here if you put that XL is equal to your what you call minus Xg, then ZL is equal to Rg minus JXg. That means ZL is equal to Zg conjugate, because Zg actually is equal to your Rg plus JXg. Therefore Zg conjugate is equal to Rg minus JXg, right. So that's why for maximum power transfer theorem, when both RL and your XL, your both are your what you call variable, then that this is the condition for maximum power transfer, that ZL is equal to Zg conjugate, right. Another one is the case 3. In this case your ZL is there but XL is fixed but RL is variable. This is the case 3. So in that case you please do it. In that case you will directly add this one, you will get Rg plus JXg plus XL. So in that case what will happen, RL will become absolute Zg plus JXL. So RL will be Rg plus JXg XL. This you can do yourself. Therefore my RL will be equal to maximum power transfer theorem, it will be Rg square plus Xg plus it is capital is taken, doesn't matter, this one is square. So this is for maximum power transfer theorem. Straightforward, we are writing like this, right. This you add, this thing and this thing you add, right. So it will be Rg plus JXg plus XL, right. So these three cases are there, right. So in the, now with this thing we will take few simple examples, 3-4 examples. Suppose in the circuit of figure 1, that is, this is figure 1, I will show you. The load ZL consists of a pure resistance RL. Find the value of RL for which the source delivers maximum, it will be maximum power, right, power is missing. So maximum power to the load. Determine the value of the maximum power P also, right. So let me clear it. So this is the circuit is given. This is 10 J20 ohm and this is ZL is given RL. That means it is basically simple RL, right. And this is the source 50 angle 0 volt. So we know RL is equal to mod Zg. So it is mod 10 plus J20. So root over 10 square plus 20 square. So 22.4 ohm it will come. Therefore I is equal to Vg upon your what you call Zg plus RL. So Zg is 10 plus J20 and RL we got 22.4. So it will be 1.31 angle minus 31.7 degree ampere, right. And therefore P is equal to I square R. So 1.31 square into RL is equal to 22.4. So it is 38.5 watt. So it is a very simple problem. Very simple problem, right? Similarly, example 2. In this case, repeat example 1 with ZL is equal to R plus JXL. RL and XL are both variable. I mean, you repeat this example while ZL is equal to your RL plus JXL is added and all data remains same. All data remains same, right? So in this case, what you can do is that to your total impedance, we know that for this when RL and XL both are variable. So my ZG was 10 plus J20, your J20. Therefore, ZL is equal to ZG conjugate. That will be 10 minus J20. Right? This we have seen in our theory. Therefore, total impedance will be ZG plus ZL. ZG is 10 plus J20 and ZL will be 10 minus J20. So minus J20 plus J20 cancel. It will be 20 ohm. Therefore, I will be equal to 50 angle 0 by ZT, that is 20 only. So it will be 2.5 angle 0 degree ampere, and P is equal to I square into R. So that is my I square is 25 square and this is 10. So it will be, that is RL 10 ohm. So it will be 62.5 watt. So only this condition, if you just keep it in mind, then everything will find simple, right? So now another thing is in the circuit shown in figure this is figure 2, right? The resistance Rg is variable. That means this resistance Rg is variable between 2 and 55 ohm. That means Rg actually, that means if you write like this, that means your Rg is lying in between this 2 and 55 ohm, right? Then what value of Rg results in maximum power transfer across the terminal AB? This is my terminal A and this is my B and this is my Rg is variable. RL is 10 ohm and this is my your Xg is J5 ohm, right? So in this case, your what you call voltage is given 10 angle 0. In the network shown in figure 3, the load connected across terminal AB consists of a variable resistance RL, right? The RL and your what you call and a capacitive reactance XC, right? So in that your what you call and which is variable between this one, just 1 minute. This one actually this problem actually I have not solved. You have to find it out. This is you find it out, right? This problem actually you find it out. This is not solved here, right? So this is an exercise for you. This you solve it, right? So now next problem is example. Answer is not given here. Answer is not given here. So this is for you actually solve it. I have not solved it here. Actually solved, but I didn't put it here. You solve it. Now example 4. In the network shown in figure 3, suppose the load connected across terminal AB consists of a variable resistance RL and a capacitive reactance XC. I will show you, which is a variable between 2 ohm and 8 ohm. Determine the values of the RL and XC which result in maximum power transfer. You calculate the maximum power P delivered to the load. This is the problem you are what you call written here, right? And this is the circuit. This is voltage 50 angle 45 degree. This is 3 ohm. This is minus JXC variable and this is RL, XC and RL variable, and this is your 2 ohm and J10 ohm. These are fixed. These two are variable, and this is the point A and this is the point B, and this is the circuit. Now question is that what is first one is to find out the V Thevenin. V Thevenin means that we have solved DC circuit. So V Thevenin means first you remove this one. Suppose it is not there, first you remove it. So as soon as you remove it, then you find out what is the current I, right? So the current I am writing here, current I is equal to your 50 angle 45 degree divided by this is 3 plus 2 plus J10, right? This is the current I, right? Because this is not there, because we are removing it, because we want to get the Thevenin one. So this is the current I. So once you get the current, so this is open circuit. I am not drawing it circuit again. So this is my VAB, this is my V Thevenin then, because this is open, this is open, this is nothing is there. So this is A, this is B. So it is VAB is equal to V Thevenin. This is my current, this is my current I into this is my voltage, that is my this is my impedance, that is my 2 plus J ohm, whatever it comes, right? So same thing is written here, 50 angle 45 degree, this 3 plus 2, so 5 plus J10, so this is 5 plus J10 into 2 plus J10 into 2 plus J10, this is my V Thevenin, right. So let me clear it. So this is my V Thevenin. We got 45.6 angle 60.3 degree. Now Z Thevenin is equal to, when this one is not there, when this point this is open, Z Thevenin means you have to short this the way you do the DC circuit. It is shorted, right. So it will be 3 ohm and 2 plus J10 means parallel. So it will be 3 into 2 plus J10, right, divided by 3 plus 2 plus J10, right. So this is my Z Thevenin, right. So if you find out Z Thevenin, so this will be my what you call Z Thevenin 2.64 plus J 0.78 ohm. Then the equivalent circuit is, this is V Thevenin 45.6 angle 60.3 degree, and this is my Z Thevenin 2.64 plus J 7.2, and both variable. RL is also variable, XC is also variable. So for maximum power, if both are variable, so for maximum power transfer we know ZL is equal to Z Thevenin, in this case conjugate, because this is Z Thevenin, so it is conjugate. So it will be 2.64 minus J 7.2 ohm. But XC is adjustable between 2 ohm and 8 ohm. Hence the closest value of XC is 2 ohm, right? Because we got actually what we call, it is 0.72, but XC is only variable between 2 and 8 ohm. So closest value is 2 ohm only, because it is 0.72. So closest value is 2 ohm. So XC is taken as 2 ohm, right? Therefore, Therefore, RL is equal to mod ZG minus JXC. We have already done it for that when RL and XL are variable. So in this case, it will be 2.64 plus J 7.2 minus JXC is equal to taken 2 ohm, right. So that means my RL will become 2.93 ohm. Therefore, ZT will become Z Thevenin plus ZL. Z Thevenin is this one, this 2.64 plus J 0.72, and your ZL will become 2.93 minus J2, because some range is given. Here you got something, here you got something, but closest value is 2, because XC is in between 2 and 8, right. Therefore, your what you call that, you calculate I now, ZT you got this value, then you get I for this one, your V Thevenin by your ZT, you will get 8 angle 73.3 degree ampere, and power is equal to your 8 square into 2.93, that is 187.5 watt. Thank you very much. We will be back again.